Hello, everyone. My name is Anna Stockstad, and today I'll be talking about this project, which is investigating the influence of soil frost and moisture dynamics on soil strength in aspen forests. I'd like to thank my fellow collaborators on this project, Rob Slezak, Charlie Blinn, Randy Kolka, Steve Sebastian, and Alan Tochkolowski. Today, during this presentation, I'll run quickly through the research questions, sampling design and results, and then end with a discussion of the implications for forest managers. So to start off, what are our two main research questions? First, we're asking, how do soil strength and frost vary by drainage class? And secondly, how do changing precipitation and soil moisture dynamics influence soil strength and frost? Now I'll give you a short summary of the project design. So this project has 24 plots in northern Minnesota located across 3 counties, Aiken, Itasca, and St. Louis counties, all located within mature quaking aspen stands. Each site contains 8 plots, which are paired plots located across 4 drainage classes, going from well-drained to poorly drained. And within each drainage class, there's a treatment and a control plot. In the summer, the treatment plot is installed with a rainfall exclusion shelter, as you can see in the lower right-hand corner. And in the winter, a snow removal treatment is installed, which you can see in the upper right-hand corner. So to start off now with some of the results. So in terms of the frost data, this figure shows frost depth in each drainage class during the winter of 2019 and 2020, where maximum frost depth is shown above each line. So the main point that I want to get across here is that the treatment plots where we were removing snow froze to a significantly deeper depth than the control plots where the snow was retained. And this was because we were essentially removing that insulating snow layer. So both snow removal and drainage class had a significant effect on frost depth. So each drainage class had significantly different frost depths, and the treatment plots were significantly different from the control plots. So the drier drainage classes froze to a deeper depth, and the wetter drainage classes froze to a shallower depth. And across all plots, the peak frost depth was reached between March and April. Now moving into the soil strength and soil moisture relationships. These figures show for the poorly drained class at a depth of 30 and 60 centimeters, the relationship, which is a weak one, between bearing capacity versus soil moisture. We can see that roughly soil strength decreases as soil moisture increases. And this relationship was also weaker at 60 centimeters depth. Same thing for the moderately well-drained class. Soil strength, bearing capacity, decreases as soil moisture increases. This relationship is weaker in the moderately well-drained class compared to the poorly drained class. And finally, we analyzed the effects of treatment, so rainfall exclusion, and drainage class on soil strength. Unlike the frost data, there were no significant differences in mean bearing capacity at a depth of 30 centimeters, and there is no significant effect of treatment. But at 60 centimeters, soil strength in the moderately well-drained class did significantly differ from the somewhat poorly and poorly drained classes. And you can see the values above each of the bars indicate the least mean square bearing capacity for each drainage class at 2 depths. So finally, what do these results mean? We can see that snowless winters will allow for significantly deeper frost penetration. Soil strength was not impacted by snow removal or precipitation reduction, but we can see that soil strength did significantly differ across some of the drainage classes. So these results can be used to identify moisture levels where compaction risk is at its lowest. And this can help us to identify ideal operating times based on the estimations of current soil moisture levels. And finally, what does this mean for forest managers? So these results tell us that well-drained sites with either no snow or packed snow would be the most ideal operability. So we should prioritize packing snow on wetter sites where there's a higher compaction risk due to shallower frost in order to promote deeper frost penetration. And then high PSI equipment would be more appropriate on drier and snowless or packed sites because these sites have a lower compaction risk due to their deeper frost penetration. And finally, summer harvesting, we should think about waiting until soils are drier in order to decrease the impact of compaction across all drainage classes. So finally, I'd like to just wrap up with thanking the Minnesota Environment and Natural Resources Trust Fund for the funding on this project. I'd also like to thank all my collaborators for all their help with this. Thank you so much.